A few people have problems with case 5. I think it's mainly calculus problems, problems with not being able to, problems with integration basically. But anyway, let me just briefly go through it and show you some of the problems you might have had. Let me change the camera first. Okay. All right, let me change the camera just a minute. Give me a sec, guys. So basically, quiz 5, you need to, I think it'd be a good idea to draw a picture. You have two variables, X and Y, and they have a joint PDF. And the question was to find the PDF of the total portfolio loss, which is S equal to X plus Y, right? And it's always a good idea to draw a picture of the line where X plus Y is equal to S, right? And that is this line here. So the line I have drawn here, this line here is the line that X plus Y is equal to S. All right, so basically to find the PDF of S, what you need to do is you need to integrate over this line. But it's also good idea to draw the line where X is equal to Y, because the reason I have drawn this line is because if you look at the joint PDF, it is defined differently. It's defined differently on depending on whether X is greater than Y or X is less than Y. And there are two regions here you need to consider. This region here, this is the region where X is less than Y. So all this, all the area here, all the area here is X is less than Y, right? Whereas this region here is where X is greater than Y. So all this area is where X is greater than Y. Okay. Now remember, the joint PDF is defined differently depending on whether X is less than Y or X is greater than Y. So whenever you integrate over this region, you need to take that into account. And that's why I gave you the hint. I mean, I didn't want to give too much hint. So when you integrate over this region, when you integrate over this line, yeah, you're basically using this equation here. Right? You're using this equation, right? Now, because the joint PDF is defined differently over this region and over this region, you need to split this into two different integrals. You see why? Because the reason I've splitted that is, first you need to integrate from 0 to S over 2, which is this part here. 0 to S over 2 covers this part. And then you need to integrate from S over 2 to S, which covers this part. Okay. So this is the hint I gave you guys. Although I didn't want to give the picture away because I thought that would be too much of a hint to give the picture. So the idea of this hint is to use the idea of this hint is to is to split the integration into two parts. One from, when you integrate from this to this, you split it into this part first, and then this part second, all right? And when the integral over this line is the first one, right? And the integral over this line is the second one, right? And when you integrate over this line, you need to use the fact that x is less than y. And when you integrate over this line, you need to use the fact that x is greater than y, right? And that's how you, I mean, I think most of you did that right. And some of you had problems with integration. I think that's something you need to sort out in the future. I'm sure, that's why I think some of you had problems with integration, so you lost marks for that. Okay, and otherwise, I think most of you have done well in quiz number 5. The next quiz. So let me get away from this just a minute. The next quiz is, let me show you. Is this one. So I already posted the solution for quiz 5, and this is quiz 6 is this one. So here the question is, you're given the CDF and you're asked to find expressions for var and ES, right? And I think this question is not difficult. So I don't think I will give you a hint for this. You shouldn't find this difficult because we did many examples of this kind in last week's class. So if you look at the videos for last week, you shouldn't find this question difficult. So I don't think I will need to give a hint for this question, right? So this is due by noon next Tuesday. And by the way, there is also a test on this date. So I sent you guys an email reminder yesterday about the in-class test, which will take place from 4 p.m. to 4:30 p.m. on Tuesday, next Tuesday, which is the 15th of December, right? And again, I will send you the marks for the in-class test on the same day. That is, so you will receive the marks for the quiz 6 and also the marks for the test next Tuesday, right? So you should, the test, as you know, is marked out of 10. The quizzes are marked out of 1 each. Okay. All right. You guys have any questions? Any questions about the test, especially about the test next week? I mean, I told you what to expect for the test, so you should know. I mean, the test will have three parts. The first part will ask you for the extremal types theorem. The second part will ask you for the conditions 1 to 3 for extremal types theorem. And the third part will be similar to quiz number 3, which you already have done. I mean, there are many examples. You should go to the course website. Once again, I will show you. I mean, you should go to the course website, which is this one, right? This website contains many examples similar to quiz 3. So for example, if you look at in each of these exam papers, there are exam papers for the last 7 years, and each of these exam papers has a question that is similar to quiz 3, right? So you should be able to practice. And also the past in-class test. Each of these in-class tests has a question that is similar to quiz 3. So you should be able to practice, right? Okay, guys. And you have any questions, guys? Talk to me, guys. You should have any questions. All right. Okay. All right. So this week I'm going to talk about estimation of var. The topic for this week. I hope you have looked at the videos for this week. The topic for this week is estimation of var. All right. So let me quickly run through. Let me quickly run through the notes. Excuse me. The notes for this week. These are the notes I had put online. I mean, in the video as well as on the course website. So in this video, in this review session, I'm going to talk about 3 different ways to estimate VAR. One is parametric estimation, where you assume that the losses come from a distribution, a parametric distribution. 2 is non-parametric estimation, which is where you assume that the losses do not come from any parametric distribution, right? And the third is a semi-parametric, which is a combination of the 2, right? So before that, I need to summarize some material from statistical methods. I mean, as you know, statistical methods is a second year undergraduate course. Some of you might have taken it, some of you not, but it's a prerequisite for this course, as I mentioned before. If theta is an estimator of theta, then theta hat is unbiased if the bias defined by this is 0. It's asymptotically unbiased if the limit of the bias is 0. Consistent if the limit of the MSC is 0, where MSC is defined by this. And these are stuff, I mean, you have taken this course, which is a year 2 undergraduate course. These are stuff from this course. Or, I mean, at the moment, this course is being taught by Professors Corbini and Strymer. But I used to teach this course a long time ago, and the material from the material for this course, my material for this course can be found in this link. Right. Okay. And the first case is the normal distribution. So if you have losses following the normal distribution, then we know from last week the expression for VAR for the normal is given by this. And you should know from, if you've taken this course in the past, you should know that MLE for mu and sigma are the sample mean and this. So if you replace mu by mu hat in this and sigma by sigma hat, you get the MLE for VAR, which is given by this this equation here. So this is the maximum likelihood estimator for value of risk under the normal distribution, right? Right. The next is the uniform distribution. So here we suppose that the losses are from a uniform. We know from last week that the expression for VAR for uniform is A plus P times B minus A. And again, from statistical methods, you should know that the MLEs for A and B for a uniform are the smallest data point and the largest data point. So hence the estimator for VAR is given by this expression here. Right, this is the estimator for VAR. All right. The next one is the exponential. I'm running through quickly because I hope you have seen this video already. If not, please look at the videos when you have time. So suppose you have the losses from an exponential with parameter lambda. We know from last week that the expression for VAR is given by this. And if you've taken this course, you should know that MLE for lambda is 1 divided by the sample mean. So if you sub this for lambda, you get this as the MLE. So this is the MLE for VAR for the exponential distribution, right? Okay. And the next one is the power function distribution. I think, so here we suppose that the losses are from this CDF. And from last week, you should know that the formula for VAR for power function for this CDF is equal to this. Now, if you follow the procedure for MLE, if you follow the procedure for MLE for the power function distribution, you will get this. You will get this as the MLE for A. Remember, there's only one parameter, which is A, right? So if you follow the procedure for computing an MLE, you will get this as the MLE, right? Now, if you sub this, if you sub this into this, you will get this. You will get this as the MLE for var for the power function distribution, right? All right, and the next case is the variance covariance method. This is an interesting method where you have the loss. X is the total loss. Xi is the loss for the ith investment. Wi is the weight on the ith investment, because the investments may be of different magnitude, so their weights may not be the same. So X is the total portfolio loss, which is the weighted sum of the Xi's. Now, if you assume that Xi's are normal independent, then it follows from the properties of the normal that X must have this distribution. X must be normally distributed with this as the mean and this as the variance. Now for this, you can compute the var by setting the CDF equal to P, as we did last week. So if you put CDF equal to P and solve for X in terms of P, this is what you get. So the expression for var, is this one. Now, to estimate this equation, you need to estimate mu I and sigma I squared, and that's what I have done here. So suppose you have a random sample of size n1 from on x1. X1 is the loss on investment 1, and suppose you have a sample of n2 on x2, the loss on investment 2, and so on. And suppose you have this sample on xm, where m is the loss, xm is the loss on the mth investment. Then it can be shown from what you learned in what you know from this course, that the estimate for mu I is this, and the estimate for sigma I squared is this. So if you sub these two in place of mu I and sigma I, this is what you will get as this is the estimator. This is the estimator for var, for the variance covariance method, right? Okay, so, and finally, the Weibull distribution method is, so here we suppose that the losses are from a Weibull distribution which has this CDF, right? Now, if you set the CDF equal to P and solve for X in terms of P, this is what you get. So the var is given by this equation, right? Now there are two parameters here, theta and beta. Two parameters, you need to estimate them, and it can be shown. I don't expect you to show this, but it can be shown that the MLEs for theta and beta are the solutions of these two equations, right? So theta hat and beta hat are the solutions of these two equations, and hence the MLE for var is given by this, right? So this is the MLE for var. So you just simply replace theta by theta hat and beta by beta hat to get this, right? So these are the 6 different parametric methods. So in each case, in the parametric methods, in each case, we have supposed that the losses come from a certain distribution, right? But now in non-parametric methods, here we don't assume any distribution for the losses. All right, we don't assume any distribution for the losses. So this is the first method, which is known as the historical method. What it says is the following: the first thing you do is you order the data. You order the data from the smallest to the largest, like this. So this is the smallest data. This is the second smallest loss, and this is the largest loss. All right. Then, according to this method, the value at risk at P is equal to the ith smallest loss if P belongs to this interval, I minus 1 divided by n to I divided by n, right? So it's a very simple method. It's known as the historical method. The next method is the bootstrap method. Bootstrap is a technique that is due to Brad Efron, is from Stanford, is a professor there. What the fundamental to bootstrap is, suppose you have these losses x1 to xn. The first thing you need to do is to compute the empirical CDF of the data, which is given by this equation that f hat is equal to this, where I denotes the indicator function. I hope you know what the indicator function is, right? All right, and if you actually plot f hat versus x, it will look like as, I don't know whether you can see this clearly, but maybe in the video I did, hopefully you can see it more clearly. It's like a step function. So every time it passes this is the smallest data. So as soon as it passes this, it jumps to 1 over n, right? And as soon as it jumps the second smallest data, it jumps to 2 over n. Then as soon as it passes the third smallest, it jumps to 3 over n, and so on. The last one will be 1, right? So it's like a staircase going up in steps of 1 over n, right? So the bootstrap method says the following: simulate B independent samples, each of size n from f hat. And there are methods of doing it. There is a function in R, in the R software, that you can use to do this. And then compute var for each of the B random samples using the historical method. So you get B different estimates for var, right? Each obtained using the historical method, which I described earlier. And the final step is to take var to be the mean or the median of the B estimates, right? Okay. So that's known as the bootstrap method. The third method is known as the Jackknife method. This is a variant of the bootstrap method, where the first step is to compute var by the historical method for this data. So as you can see, this is x2 to xn. So I have removed the first data point, right? And you let this to be the estimate obtained using the historical method. And the second step is to do the same thing, but removing the second data point. And the last step is to do the same thing, but removing the nth data, the last data point. So after all this, you will get n different estimates for var. So the final step is to take the mean or the median of the n different estimates for var. And that will be the final estimate for var, right? Okay. Right, that's the Jackknife method. And the final one among the non-parametric methods is the kernel method. I don't know whether, had you guys done kernel estimation before? Maybe or maybe not, I don't know. Well, anyway, if you have a random sample on losses, all right, the kernel estimate for the CDF is defined by this equation here, right? Where h is known as the bandwidth and g is the integral of k, and k is known as the kernel PDF. Usually k is taken to be the standard normal PDF, right? And so this is kind of a smoothed, remember the empirical CDF is a staircase version of the data, of the CDF of the data, whereas f hat is a kind of a more smoothed version. It's a smoothed version of the CDF of the data, right? And here h, which is the bandwidth, controls the smoothness of f. The larger the value of f, the more smooth it will become, right? So by choosing different values for h, you can control how smooth this is as a function of x, right? All right, and there are, once again, there are functions in R. There are functions in R for computing f hat, right? Okay, and the next is, right, this is, so once you compute once you computed the f hat, there are two ways of computing var. The first way is as the root of this equation, where f hat is f hat of x equal to p. And the second way is as this expression here, as the sum of f hat times the ith smallest loss divided by the sum of f hats. Right here, yeah, these are the losses arranged in the increasing order. So this is the smallest, the second smallest, and so on, right? So for this kernel method, there are two different ways you can compute var, this way or this way, right? So these are the four methods. These are the four methods for computing var non-parametrically. Now, finally, I will talk about two different methods for semi-parametric estimation of var. The first is the GV method. You may recall what GV is. GV is the distribution of extreme value under definition 1. Remember definition 1. I gave you three definitions of extreme value. Definition 1 is the first one I talked about. So under this definition, the distribution of extreme value is given by this. Right? So to find the var for this, you set the CDF equal to P and solve for X in terms of P. So this is the expression for var. And in this expression, there are three parameters, mu, sigma, and psi. Right? And I will estimate psi by this equation. And this is known as the Hills estimator. And this involves only the data. If you look at this equation here, there's nothing else but the data, right? Right, so psi hat is a non-parametric estimator, right? Because it only involves the data, right? And then I will estimate mu hat and sigma hat as the MLEs of mu hat and sigma respectively, right? So therefore, mu hat and sigma hat are parametric estimators because I'm using maximum. I mean, remember, MLE by definition assumes that the data comes from a distribution. So these have to be parametric estimators. So of the three parameters, I'm estimating psi hat. I'm estimating psi non-parametrically, right? And I'm estimating these two guys non-parametrically. And hence, this, what you have here, is a semi-parametric estimator of var, right? Okay. I will be finishing soon, so and do some examples. So just bear with me, guys. The second of the two methods is the GP method. GP stands for generalized Pareto, and this is generalized Pareto is the distribution of extreme value under definition 2 of extreme values. You remember this? This is definition 2, and under this the CDF of the extreme value is given. But you may recall this from a long time ago, right? Now to find the var for this, you set the CDF equal to P and solve for X in terms of P. So this is the var. Now here again, there are two parameters you need to estimate here, sigma and psi. I will estimate psi using this equation, which is once again the Hills estimator. And I will estimate sigma hat as the MLE, which assumes, MLE by definition assumes that the data comes from a distribution. So sigma hat has to be a parametric estimator. So this is a non-parametric estimator, and this is a parametric estimator. All right. So hence, guys, that the estimator for var given by this is a semi-parametric estimator of var. All right. So these are the notes I covered in the videos for week 7. Now let me do some examples now, because I've done no examples so far, right? All right. Okay, let me do some examples just to clear up so you get less bored. I know some of you, so this is example 1. I mean, this is. I think this is one of the question from one of you. One of you guys asked me to do this question, so that's why I'm doing this. So you have a random sample from a uniform distribution A to B. The question is to find the MLEs of A and B. This is stuff you should have done in your statistical methods year 2 course, right? Right. The first thing you need to do is to write down the likelihood function. Right. This is the likelihood, the product of the density function. So this will be 1 divided by b minus a to the power n times the product of the indicator function. The indicator function means, it simply means that if xi lies between a and b, if x lies between, this should be a guys, not ai. Right? If xi lies between a and b, it is equal to 1. Otherwise, it is equal to 0, right? Okay. Now, now you can simplify this, guys. If you simplify this, you will get okay. Right, so this is the likelihood function. Now, in order to find the MLE for A and MLE for B, what you need to do is to draw a graph. You need to graph, well, you need to draw 2 graphs, by the way. I know you can only see 1 graph right now because I'm drawing it. So you need to draw 2 graphs. The first graph is the likelihood versus A. The second graph is the likelihood versus B, right? Suppose, okay, let me take 2 points here. Suppose this is the minimum of xi, and suppose this is the maximum of xi, right? Suppose this is the minimum. Right. Now, can you tell me how the graphs will look like? I mean, this is stuff you should have learned. I'm sorry. I'm just repeating year 2 stuff, but how would this graph look like, guys? How would this look like versus likelihood versus A? In other words, I'm asking you how the graph of this as a function of A when B is fixed. It says A must be strictly less than equal to, I mean, a minimum must be greater than equal to A. In other words, A must be less than equal to the minimum. So what that suggests is that, if A is greater than if A is greater than the minimum, then it is 0, right? And as A as A increases, minus A will decrease, right? And 1 over this will increase. So your graph will look like this. Do you see why? I mean, it's simple math, guys, that, right? Because if A is strictly greater than this, then it has to be 0 because of the indicator function. And this guy here, as a function of a, is an increasing function, right? And over here, b is greater than or equal to the max, right? So that means if b is less than max, then it has to be 0. So this side here has to be 0, right? And this guy here, as a function of b, if b increases, 1 over this is going to decrease. So your graph will look like this, right? So from this graph, you can see that the largest point of this graph is over here, and the largest point of this graph is over here, right? So hence, from this graph, you can see that the MLE for A is the minimum of xi, and from this graph, you can see that the MLE for B is the maximum of xi. Remember, the MLE is the point where the graph reaches the maximum, right? And here the graph reaches the maximum at minimum of xi. So A hat equal to this. And here again, the MLE by definition is the point where the graph reaches the maximum, right? So here the graph reaches the maximum at maximum of xi, and therefore B hat is equal to the maximum of xi. All right, guys, so this is year 2 stuff, but I mean, if you still don't follow me, can you please Zoom me in person, or call me, or Skype me, or comments, or meet me in person. I'm not far from the uni, so you can meet me wherever you like. Okay, all right. All right, so this is example 1, guys. All right, the second example, is this okay with you guys, or any questions on this example before I go to the next one? Hello, guys. Talk to me, guys. Is this okay or what? Okay, thank you. All right, the next example I'm going to do is the following. Example 2. Right. So here we have we have a random sample from this CDF, right? X is greater than 0. We want to find the MLE of this guy here. So the first thing you need to figure out is the MLE part. So you need to set this equal to this, which implies that okay, and this implies that right, and this implies that 2x plus right, and this implies that ax squared plus 2x plus log okay So what you have is quadratic equation. So x equal to minus b minus 2 plus or minus b squared, which is 4, minus 4ac, which is 4 times log of 1 minus p divided by 2a. Now, which one is valid? Which is it, plus or minus, guys? Hello, guys, talk to me. The valid root is, hello, are you listening to me or what? You have plus or minus. You have two different roots. So which one you think is valid? Remember, x has to be greater than 0, right? So if you put minus, what you have is a negative number. So the plus, so the valid root is the one with the plus. So it has to be minus 2 plus, you can take the 2 outside, it's going to be 2a, right? So this implies that the var is equal to minus 1 plus all right, so this is only half of the problem. Now what you need is, we need to find the MLE of what. All right, so the first thing you need to find is the to find the MLE, you need to find the PDF, right? The PDF is gonna be, it's gonna be 2 plus right. All right, this is the PDF. You can pull out the 2 outside, so this will be 2 times 1 plus right. Okay, right. The next thing is, all right, the next thing we need to do is to write down the likelihood function, right? So that's what I'm going to do. Uh, right. Now you should take the product, you get 2 to the power n. Correct me if I'm wrong. It's possible that I might make mistakes. I from 1 to n of 1 plus a, yeah, and then to sum of xi a. Okay, so this is the likelihood function. Yeah, so the next thing you need to do is to take the log of the likelihood function, which is gonna be yeah, minus 2 times right, and the derivative, the next thing you need to do is to find the derivative with respect to a is if you differentiate with respect to a, you get this is what you get, right? And so the MLE of a is the root of the equation that right. Okay, now in order to prove that the root of this is actually an MLE, right? Let me call this star. Let me call this equation star. You need to show that the second derivative of this with respect to a is negative in order to show that that the root of this equation is an MLE. You need to show that. So I'm going to take the second derivative of the log likelihood with respect to a. So you get the derivative of this, right, which is which is gonna be minus okay, and this is clearly less than 0, right? Hence, hence right, hence the root of hence the root of star is the MLE, right? So now to answer the question, to answer the question that we want the to answer so to answer the question about the question was about hence the MLE for var is given by this, right? Where they had. They had is the root of star. All right. So that completes example number 2. I wished I had more time to do one more example, but I think I run out of time for today. So you have any questions, guys? Hello, you have any questions? So on Thursday this week, the tutorial sheet for Thursday will be the same as the tutorial sheet for last week. So I will do the remaining questions on the tutorial sheet for last week this Thursday, right? All right. Any questions on this, guys? Do you have any questions on this? Hello. All right. Thank you, guys. All right. So I'll talk to you again on Thursday. And if you have any questions about anything, especially the test on next Tuesday, contact me 24/7 by Skype or Zoom or phone or email. Okay. I'm also happy to see you in person wherever you want me to see you. Okay. All right. Take care, guys. Have a good day. Have a good evening.